So today we're going to talk about database concepts. Okay, so we're not going to go too in depth. I budgeted 2 hours, but we'll see if we can get it done in 1 hour or so. Um, First off, we talked about introduction to computer science. Software and hardware was the next thing we talked about after talking about the IT career paths. We talked about building websites, web applications, and internet on the web. Last week we talked about cybersecurity. So today is about databases. So I really apologize for the rough start this today, but we'll try to go through everything as fast as possible. So today's session, we're going to cover a few things. We'll talk about the definition of a database. What is a database? We'll also talk about the problems that arise in normal in life that databases come in to solve. So the solutions that databases provide, and then we'll talk about core concepts of databases. We'll move on to talk about types of databases. A little bit of a history, but talking about the relationships and in relational databases. That's all in the core features, as well as talk about transactions, database transactions that take place. Finally, we'll also talk about the main differences between relational and non-relational databases and talk a little bit about the language that is used to communicate with the database, which is known as SQL. So we'll talk about SQL and a different part of a different version, which is known as NoSQL. I'll just call it that for now, as well as new SQL. Okay. So do we have any questions so far on that? Again, all the pictures don't want to show up. So since all the pictures don't want to show up, I'll just end up using the notes which I had. That's not going to be really interesting, is it? But yeah.
Can you please increase the font size if possible?
Yes.
Is it possible?
So can you see it now?
Thank you.
Is that better?
Yes, much more better.
Awesome. So can anybody tell me what do they think is the definition of what a database is? What do you define a database? Beatrice, can you tell me?
Um, let's say an organized collection of information or data.
Yeah, yeah, yeah. That's good. That's good. That's pretty much what everybody thinks about the very first time when you talk about databases, right? Like database is just a repository, but we don't want to just see database as a repository. Here, let me go ahead and I'm going to see. I really am struggling here to get those
Images.
yeah, to get the images because it's definitely going to help us quite a bit. Let's see. I'm going to force it. There's no way I can do it without the images, so I'm going to force it here. And yeah, let's get databases. Okay, so let's try this. Let's see. Okay, so this should work. Okay. Yes, so databases, one thing we need to know about them is that, you know, we are not just going to talk about databases, talk about other things too, like data analytics, big data warehousing, modeling, and so on. But databases are not just what are known as, so if I open this, will I be able to move? No, I'm not able to. Okay, so I'm going to just drag this over. All right. That's better. So can you see my screen now?
Yes.
Awesome. So databases are not just a collection of data, right? They are not just a repository. They are not just where we're going to have data and store data. Okay. If I ask you, for instance, what is an engine? You're not going to say an engine is just a collection of parts, right, in a car. The engine actually has a lot more than that. It's true that it's a collection of parts, but it's more accurate than that. It's true that a database is a collection of data, it's a repository, it's where you save information, but it's more than that, because after you have saved that information, what's the next thing? It's going to grow, right? For instance, if you save one user in your school database, you're going to have more new users every time. If you save one user on Facebook, you're going to have more people signing up on Facebook, right? So your data is going to grow. That's some of the things that a database can accommodate. Your data is also going to change over time. Maybe you want to change your name, or maybe you want to change your location, or you want to change your profile picture. All those things change, and a database has to be able to accommodate that, right? Not only accommodate the change, but also maybe remember the last value that you had. Because one reason or another, you may want to change it back in future, or you want to track your changes, see how many changes that you have done. Okay. Now, in other cases, maybe your data is being stored in Cameroon, but you also want that data to be able to be accessed in America. So your data needs to be shared, right? Or maybe you're storing the bank information at one bank, you need it to be shared with another branch, for instance, or maybe you want it to be shared with another colleague, or maybe just a team and not the whole world. So then you want to be able to share that data found in a database. And if you're going to share it across the whole world, you probably don't want to wait for the post office to take the information from one place to the other, or a car, or a airplane. You want it to be fast. You want your data to be transmitted fast. And if you have a bunch of data, let's say you have Facebook with millions or billions of people on there, you want to be able to search that data also. You want it to be reliable. If somebody is going to remove money from their account, you want every bank that you have to show the same account balance. I don't want to go to the bank in Limbe and the bank in Limbe is showing me one amount, the bank in Douala is showing me another amount. It has to be reliable, it has to be interdependent, it has to be consistent, and you have to also protect and secure it, just like how we were talking about cybersecurity last week. So all of these things are the things that actually make a database unique. Does that make sense?
Yes. Yes, it does.
Yeah, so it's not just about, storing data, it's also about processing it, storing it, processing it, analyzing it. Okay. So database allows us to do all of that all together. Now, the way it happens is because a database usually is made up of a database management system. Okay. So this is a software that is used to create, define, and manage a database. So DBMS is short for Database Management System. There are many of them out there. Okay, there is Microsoft SQL Server, there's Oracle Database, there's IBM DB2, and so on and so forth. Okay, now if we go back to one of the previous pictures that I had earlier, it was talking about the life cycle, the stages of getting a database. Yes, go ahead, Beatrice.
Um, what's SQL?
Okay, we're definitely going to get to that. We're definitely going to get into that. Very good question.
Right.
So let's park that for now. But SQL stands for Structured Query Language. So we're going to talk about that briefly. But right now, I just wanted to point out to you that a database normally, you have some people sit down. Maybe, Beatrice wants to open a library. So I want to maybe help her out, and she comes to me and says, I need a database to be able to track all the books in the library and so on. So I have to sit down now and design that database or create a data model to be able to answer that question. That's one of the problems that you need. If Joe wants to create a movie theater, or he wants to start renting movies, Nigerian movies, then I can create a database with all the movies in there to show who is renting which movie and maybe customers and so on. So that part is where you have the designing of the database. And then after you've sat down, designed it, drawn all the pictures and or drawn all the logical schema, you then go to create it, create and implement it. Then you have people in operations, maybe you have a software developer or designer that can design that database or write queries that are going to be able to integrate that database with an application. And then you have to keep maintaining it, monitoring it, and evaluating it to make sure everything is working okay. So this is what actually happens before you create a database. And let's go back to where we were. We're talking about database management system. So this software is going to create, define, and manage your database. And Microsoft SQL Server. SQL again stands for Structured Query Language, which is a language that we use to communicate with the database. Because obviously the database does not understand English, French, Spanish, and so on, German. So we have to be able to write code that is going to go back to the database and ask questions, ask queries, of particular what in particular what we are trying to achieve. For instance, you want to see how many books do you have in your library? How many books were borrowed yesterday? How many books are still outside that have not been returned? How many categories do you have for your books? And so on and so forth. All those things, you can get those answers or those questions answered by writing SQL, the structured query language, to go into the database and give you results. Does that answer your question, Beatrice?
Yes, yes, it does.
Okay, but we'll still talk about it in depth in a little bit. Okay.
All right.
Awesome. So these are all some of the database management systems. One thing is they all have in common many, many things. Okay. We've talked about history a long time, from the beginning. Obviously computers started in the 60s, 70s, the different generations and so on. By the time it was 1979, Oracle released their own version of a database. IBM came around and released DB2. Microsoft got into the picture around 1989, and so on and so forth. So these are the major database management systems, the major products that have been created. These are like the old school ones, but they all have very common things. They all have these core features that are common amongst them. And also one thing that they all have together is that they are all relational. So you're going to see R in front of them a lot. R stands for relational, and that makes it to become a relational database management system. Because when you create it, let's say for instance, if you're creating a database for a school, the teacher is usually related to a class or related to a student to a class and so on and so forth. So that relationship between the things that you put in your database is what makes it a relational database. Does that make sense?
Yes.
Yeah? Okay, good. So those old school databases were all relational database. Now, normally you're not just going to have one database for your whole organization. You might have one database for human resources stuff, another database for the purchasing, for sales, maybe, another database for finance to track your finance stuff, another database for customer relationship management, how you interact with your customers, and maybe another database to host all your website stuff. So all of these databases are usually going to be hosted on a machine. That machine is known as a server. Are you guys familiar with what a server is?
Yes.
Yeah, so a server, the computer that you're using, is usually known as a client. Okay, the client usually reaches out to the server to get information. So in most companies, they're going to have like a server room if the server is on the premises, or it could be on the cloud, which we're going to talk about cloud computing next week. So normally a server will be like a compound. You have a compound. In that compound, you have many different houses. Or let's say your server would be a whole country. In that country, you have different regions or different states or different provinces. Okay. And then within each one now is a database. So all of that are usually managed by one server. And obviously, you want to replicate the server so that if the server goes down, another server can jump in and all your processes will still be working just fine. Make sense? Any questions?
Yes, I have a question.
Yes, go for it.
Does it mean the server stores the information of all the different databases?
Yes, more or less. So let's look at it this way, right? If you have a plot, your plot will be like your server. Within that plot, you can decide to have just one house, or if it's a big enough plot, you can have 10 houses in there. Each house is independent of the other house. Does that make sense? So each of the houses now will become a database within your plot, within your compound. Okay. So this
Okay.
Yeah, so the same then with a server. A server is just a dedicated machine. Instead of it being a client where you can run programs on there, you can run Word, Excel, you go to the web browser, go to websites, and so on. You don't do that on a server. The server does not really have a display. A server is just a machine for you to be storing particular stuff on there. You can store databases on there. You can store, a database for a website, a database for different areas, and so on and so forth. Okay, so again, so it's not just for storage, it's for storage and also for transfer of information, processing and analyzing all that information. Okay, so
Okay.
think about it as a dedicated space for you to store and process your information. All right, awesome. So now in the recent years, we don't only have to deal with relational databases. There are new databases that have been created. In the 2000s, you have Hadoop, Couch Database, Neo, Cassandra, Redis, MongoDB, and so on and so forth. I mean, the databases are being created more and more. These ones are really not relational databases. These ones, most of them use NoSQL and so on because they have particular needs that cannot be, oh, jeez, I think, okay. They have particular needs that need to be answered, right? That cannot be addressed by those relational databases in the past. Okay, does that make sense? Is
Yes.
everybody with me? Okay, so now that we have those, we've talked about that. Let's see, let me go ahead and proceed. So, how do you create a database? Again, like I said, if it's like a store, you can decide to create a database. And then within that database, the database is going to have the most important thing in a database is a table. Okay. So tables again are the ways in which you're going to set up your data. You can decide that you have a store and you're going to create a table that's going to save only the customer information. You get another table that's going to save just your products, another table for all your orders, another table for payments, and so on and so forth. Each of these databases are made up of tables. These tables are what are usually related to one another. For instance, a customer can be related to a product once they have they have bought that product, and then that product has been added to their order. So a customer can have an order, maybe an order number, a customer number, and then when they make a payment, they also have a relationship with that. So that's how you break down a database. If it's a database for, say, a school, You can decide and say, okay, that school is going to have teachers, instructors, the school is going to have students, the school is going to have classrooms, the school is going to have courses, and the school is going to have events. So you have to create a table for each of these entities. We don't want to use the word thing, we're just going to use entities because it's more appropriate. So when it's time for you to create that database, when you sit down and do your logical schema, modeling and design, you then decide what are the tools or what are the entities that are going to make up this real world scenario. If it's a library, then it's different. You're going to have books, maybe you're going to have borrowers, maybe you're going to have different sections for the books, maybe you're going to have events as well, and so on and so forth. So there are very different databases for different setups. Okay. So first, one thing I forgot to mention is that databases are usually denoted by a cylinder. Okay. So this cylinder, the blue drawing in the back. Let me go back actually. So as you can see here, these are all cylinders. These are all different databases. The cylinder is a icon, is a symbol of a database. That's because back in the days, databases usually used to be disks. They usually pile disks on top of each other to store that information. That's when, if you had to pile them together, it would probably be taller than a story building to be able to save information for just me and you. But now data got, storage became something easier to manage because you can actually buy small, flash drives or memory cards that can store up to how many gigabytes. But back then, this disk of a big size, bigger than my head, could store maybe 8 megabytes, maximum of 200 megabytes. But it's not the case now. So just to point out to you that if you see that icon a lot, that's because it signifies a database. Okay. So as you can see in here, the database has multiple tables. You have your customer table, product table, order table. All of these tables are being defined in a purchasing database. But what is a table made up of? Has anybody in here used Excel?
Yes.
Microsoft Excel, right?
Yes.
So think of Microsoft Excel like a table, okay? So each Microsoft Excel, you have, rows and columns, right? So if you look at a table, the columns, just like the columns that are holding up a building, the columns usually signify one piece of information about somebody, and the rows usually signify one record. So the row is a record and the column is a field. So think, for instance, if you're going to make a passport or an ID, they're going to tell you to fill a form. Every space in that form is a field, but the entire form that you submit is a record. So if there are 20 people there to create an ID, there are going to be 20 records that need to have all those fields filled out, and then they're going to insert them in a database. Okay, and it looks something like this now, which is similar to what we see in Excel every day. So the table, for instance, this is a customer table. You can see Melissa Zimmerman is one record, but this record has about 5 different fields. They have phone numbers, they have email address, they have first name, last name, and so on. Okay, so that's how you create a table. And the table is made up of rows, which are records, but each of these columns have to be defined. When you want to create a table, you have to define the columns of that table. This customer table is going to have 5 columns. The column is going to have a given name. In this given name, I want it to be able to take just a text that you can enter. I also want family name, and I also want it to take a text that you can enter. I want email address, and I want it to take the person's email. I also want phone number, but I want it to take only numbers. A phone number cannot have letters. So that is going to be an error for the database. You want build your database so that it has consistency, reliability, and so on. There's no duplicates and there's also accurate information, because remember, we are not just storing the information. We're going to need to share it. We're going to need to modify it. We're going to need to transfer it. We need to be secure, and all those things that we talked about in the beginning. We also have postal code. So that's how you create a table with the rows and columns. Now you can have a customer table which is gotten its own key. For instance, you have a particular way that you can identify a record. If it's your ID card, maybe they have a particular ID card number or maybe a record number. If it's a patient, obviously you might not want to have email to specify. Maybe they want to set the email to be that primary key. That's what it's called. But if it's a membership for maybe a gym or for an organization, then the user ID will be something that will be unique. So normally each record is identified by a unique key. A unique key, just like they cannot have 2 or 3 people with the same passport number or the same ID number. That's how you create keys to identify each record. That way it is unique. Those keys is what we call primary keys. Okay, so you usually have a particular column, a particular field that contains unique values. The value never repeats itself, because if I want to identify a particular person, then I have to go ahead and use that primary key to identify them. Okay, does that make sense? Any questions so far? No questions? Awesome. So then when you use that primary key, again, if you're looking at a list of customers, maybe their email is unique. Their email is probably unique, so we'll use that email as their primary key. Or if you're looking at cars, cars usually have VIN number, vehicle identification number. And the vehicle identification number is never going to repeat itself for any cars. So you might use that as well to identify the cars in your database. In some cases, you generate a key. So if I create a database, I know there are no records in the database, nothing in there. But then I want to be able to start tracking the database. Now I want to be able to see what's going on and what's not, the new changes that are taking place. In that case, I can start a generated number. I can decide and say I want to start generating a number from 1 or from 100 or from 1000, and then each time it's going to generate a new number for me. If I add a new person in that database or a new record in that database, the generated number is going to increase by 1, or I can set it to increase by 2, or any number, set it to increase by 10, and then that's how you have a number that's never going to repeat itself, because it's generated automatically by the relational database management system. Does that make sense? Everybody good so far? Still, is anything confusing yet?
Please, can you take that again?
Okay, so you can decide, instead of using a particular field to be your primary key, to be the unique value that identifies. Maybe somebody can come and, let's say I'm using a bank. I created a bank database, and then you come and sign in, and I said I'm going to use your email as your unique number. And if you come back tomorrow and decide that you want to open another account, I cannot force you to go and open another email account, because you cannot use that same email account you used the last time, because that was your primary key. So the best way to do it is for me to generate my own numbers, generate my own values. Each time I add a new account, a number gets generated automatically for me. But I know those numbers is never going to repeat. The numbers can go to 1 million, 1 trillion, or whatever number. So you create a generated primary key for you to be able to use as your unique value to identify each of the records. Make sense? A little better. Okay, so let's take a look at some of the things that happen when you do that. So you can use that primary key to create a reference, to create a relationship. So for instance, you have a customer which has a customer ID. As you can see here, this is a customer ID, and the customer ID for Leilani is 567. Okay, but then you also have orders. Each of your orders have an order ID, the date that the order was made, the amount that the order was made for, the terms, whether it was paid, and so on and so forth. And then instead of us having all the information about the customer that made that order, we are just going to have the customer's ID in there, and that's enough. Because that customer ID is unique. It's unique only for that customer. Now, if we need to pull information about that customer, we can use that customer ID and extrapolate it to find what the relative number is. Does that make sense?
Yes.
Yeah, so it's unique. Nobody else is going to have 576. Sorry, 567. 567 is always going to be Leilani Santos. So we know that she is the one that placed these two orders because the customer ID in this table, which is a foreign key, matches the primary key in another table. So when you do that, you create those tables to have a relationship, which gives you that name, Relational Database Management System. Okay. So those two, and then yes, yes, go for it.
So if this customer, let's say he moves out of your bank or something, the reference still there, or you could delete it to give the number to another customer. Is it possible?
I did not get the question clearly. You were breaking up a little bit. Can you try asking it again?
Okay, you said this reference 567.
Yes.
You put it to the system, the whole information about that particular customer. So what if the bank, say, decides to close the account or any other thing, go somewhere else? Or is it possible for another customer to have that same reference?
Okay, very good question. I understand your question now. So if Leilani is 567, she decides that I don't want to be in this bank anymore. She leaves. Can we reuse that same customer ID? If you're going to, that's a very good question. If you want your database to be very good, you don't want to reuse it because what will happen? If you reuse it, you're going to lose your historical data. Since you have unlimited numbers available to you, it's better for you to create a new account each time, start a new relationship with that customer rather than, delete it. Normally, we'll talk about this very shortly because that's some of the things that you can do in a database. Normally, you don't even want to delete it because when you delete it, you're going to lose a lot of information. Remember, we are tracking the changes. Okay, we want to not only store the information, we want to also be able to change it, modify it, analyze it. Tomorrow, if somebody comes in and says, how many customers did you have in 1999? You'll not be able to count Leilani because you have deleted her from the system or you have changed her number. Now somebody else is using that number. But if you start a whole brand new number and then start putting Vitus is now a member of that, now a customer in that customer table, then they need their own ID altogether. The same with school. When let's say you go to UB or University of Yaoundé or University of Bamenda, you get given a student ID. For instance, I had a UB number. I'm the only one that's going to have that UB number until I die. You cannot reuse it. The same with your ID number. The same with your passport number. You cannot reuse it because that's your personal identification. Numbers are just going to keep increasing. Does that answer your question?
Yes. Thank you.
Awesome. Very good question. Okay. So now you can see that the relationship then is built that way. When you have a database schema, when you sit down and try to talk to your person that wants you to create a database, that's how you build a schema diagram, a logical diagram to explain what the database will hold. For instance, you're going to have a customer table, right? The customer table has all these columns. The columns are customer ID, first name, last name, company, and so on and so forth. And that customer ID is the primary key. But then you also have an order table because customers are going to place orders from your store. Your order table is going to have an order ID, it's going to have a date, amount, all the things that you see in your receipt. Think about the receipt that you see at the market or supermarket or wherever you go to buy stuff. All the information that shows up on there is being printed from a database. Okay, so it shows all of that information. The order ID, there's usually an order ID in there which is unique, so they can always go back and track or trace your order. The order ID is unique for that table, so it's the primary key. But the customer ID is being pulled from another table, so it's a foreign key. And now you see the items that are ordered. Okay, the items that are ordered, you usually have the ID number, which is pulled from the order table. The customer number you don't really need in that case because it's going to be tied to the order. But you have a product ID, which is also a foreign key from the product table because the product is just the things that are being sold. Okay, the thing that is being sold has a name, a color, a unit price, weight, and so on and so forth. So that's how you go ahead to build uh, a schema diagram or a model for a database. Okay, does that make sense?
Yes.
Yeah, so you don't only build it and it stays that way. You go back and evaluate it and make changes. Because tomorrow somebody will come in and say, this stuff has a color, it has unit price, but now we want to change the price. We want to have a discount price. So maybe you have another, add a new column in there, discount price. Or maybe add another column in there. Is it on discount? Yes or no? So if it's on discount, you're going to show the discount price. If it's not on discount, show the regular price, and so on and so forth. Okay, so that's how you build a database. But there's going to be times that we need to pull this information out of that database. We don't only want to save the information in the database, we want to also remove the information from the database to create reports or put it on our website or give the customer feedback and so on. There is where we use SQL, which is structured query language. Okay, so what is structured query language? It was originally called SQL. So you see people who still call it SQL, but SQL is not being used because of trademark or copyright issues. I think some other guys had that word copyrighted, so they use SQL right now. But we talked about relational database management systems, right? All the ones that we talked about, there are a few of them that even have SQL in there because SQL is very important. You have Microsoft SQL Server, you have MySQL, you have PostgreSQL, you have SQLite. These are all derivatives because these are all relational database management systems that are using SQL in their name. So we talked about those tables. The tables are the units, the most important piece of a database, okay? The primary object of the database. Tables can be joined together. You can join 3 tables, 2 tables, 5, 10 tables, depending on how you want to do it, how complex it's going to be. You can join them to have a combined result and then display that information nicely. For instance, you can have the order table joined with the customer table to show the customer and their orders and so on. Does that make sense? Everybody good with that so far?
Yeah.
Good. So that said, Let's talk briefly about transactions. Everything that you do in a database is known as a transaction. Whether you're adding information, you're removing information, you're changing information, those are what is known as transaction. One other thing that we haven't mentioned is CRD, CRUD. Okay, we'll talk about that shortly, but let's talk about transactions here. When you make a change to the database or when you add or remove stuff from the database, we have to make sure that you're doing all of it or none of it. That's what's known as atomic. So you cannot go in and make a change in the database, half of it is done and half is not done. It does an all or nothing rule. Okay? You want to make sure that the change is consistent. The database is valid before and valid after. What is a consistent change? If they tell you to enter your date of birth and you go in, instead of entering valid information, you go ahead and try to enter next week as your date of birth, it's going to give you an error message because it's not consistent with what the constraints are. If you're being asked to enter a salary, okay, and you go in and enter a number, or sorry, enter a word, let's say enter a word school, instead of adding a actual number, then it's not consistent with all the other information that's on that column. The column that needs to match what the data type is. Okay, then it's isolated. So no one was half completed result, or no one sees half completed result, because once you make a change or affect a transaction, it does not depend on another transaction. It happens by itself once and for all completely. And also it's durable. What is meant by that is, if today you have made a change to the database, they turn the light off, they put the light back on, that database is going to stay the same way you made your change. It's durable, you don't lose data. Whether the power goes on or off, your data stays there. Does that make sense? I hope so. Everybody's on mute. Now, let me go back to my notes. I want to make sure that I'm not skipping anything. Okay, I need to escape out of this first. Where is it? Where is it? Okay. Awesome. So there. So far, we've been able to talk about the definition of what a database is, the problem statement, the problems that it solves. We talked about some core features. We also talked about the database design, model, and schema. So we just talked about ACID, which stands for, can anybody remember what ACID stands for?
Atomic, consistent, iterated, durable transaction.
Very awesome, very awesome. Let me go ahead and write those in there so that we can all remember. So we did say a transaction has to be ACID. There we go. So an ACID transaction means
Atomic, consistent, iterated, durable transaction.
I thought I was typing. I don't see where am I making a mistake somewhere? Let's see. There we go. Oops, that's what I did. I used the tab. Okay, transactions are atomic, consistent. So if your column is taking only numbers, you need to enter a number. If your column is taking only dates, you need to enter a date. Okay, it's isolated, so when you make a change, It does not depend on another change. It does not depend on anybody. The change is done. And it's durable. Once it's saved. Whether the light goes on and off, whatever happens, you break your computer, the data is still going to be there. So that's what we talk about transactions. Now, we talked a little bit about relational and non-relational databases. We'll talk more about that and also about SQL. But I also did mention, let me go ahead and type ACID right there. I also did mention about CRUD. CRUD is create, read, update, and delete. So those are the different things that you can do with your data. You can create new data in your database. You can create new records, right? You can create new tables. You can even create new databases. And now you can also read the data within your tables. You can also read the number of tables that you have within your database. You can update them. You can update your table and say, okay, I want to add 2 more columns. Or update your table and say, I want to change this column or I want to remove this column. You can also update your data. Maybe you want to change your favorite color from blue to red. All of those information, you can do it. Or you can also delete. Maybe you made a mistake and entered wrong data. You want to delete the record altogether. So those are the 4 major things that you can do in a database. And in order for you to be able to do these 4 things, you need to use SQL. So SQL stands for Structured Query Language. Just like everything with a computer, we cannot tell the computer, hey, add Vitus to this class or add this class to this university. No, you have to write a code. You have to write it in code so that the computer will understand, because the computer only understands machine language. So SQL is a language that is being used to modify or deal with databases. Okay? Make sense? So
Yes.
let me go ahead and continue again with where we were. So what is a relational database? A relational database is exactly what we have talked about from the very start. These are databases that have tables. The tables are related to one another, and you can use SQL, structured query language, to be able to create, read, update, and delete records within the table. Okay? So most of those databases that we saw in the beginning of time, Oracle, Microsoft SQL Server, IBM's DB2, PostgreSQL, MySQL, and so on and so forth, those are relational databases. With those, we can use SQL to ask them any question, they will tell us. If you want to know how many members are on Facebook or how many friends you have and so on and so forth on Facebook, you use SQL to get into their Facebook database and ask the question. It's going to give you an answer. You just need to learn how to write it, understand the syntax. Just like if you go to France, you need to know French. You need to learn how to speak French before you can interact with the people in France. If you go to Germany, you have to learn German so that you can interact with them. The opposite of relational database is non-relational databases. In this case, data is not being saved in tables. It does not use SQL. It's not all that organized, as we've talked about, because they have other things that they care about. It doesn't really answer the question of that scenario. The other things that they really care about, we'll talk about that very shortly. Now, non-relational databases are usually known as NoSQL. Okay? NoSQL does not mean not SQL. It actually means not only SQL, because these databases, they also do SQL stuff in addition to particular things that shape a particular, let's say, a particular business. So if your business is capturing documents, then you probably want to use MongoDB, because MongoDB is a document database. Let's say if you're working for the government will probably not have much use for the relational databases that we've talked about, because relational database is saving what, text and numbers and stuff like that. It's not saving documents, but we want to be able to attach documents to records. So if you go to a ministry, they should be using maybe MongoDB, because when people come and filing their documents, you want the documents to be in there. So that is not something that we can really use SQL. Okay. A Redis database makes use of a key value pair. Key value pair, think about like a dictionary. A dictionary has a word and a definition. The word is a key, the definition is a value, and so on and so forth. Okay. Cassandra, again, is another example of a non-relational database. It uses wide column store. Neo4j is another example. It's using a graph database. So those, you can still use SQL to query some areas of these databases, some pieces, and some answer some questions. But you are not only using SQL. It's not only SQL. You can also use other ways to gather that information, ask that question. So that's the difference between a relational database and a non-relational database. It doesn't only depend on that. Does that make sense? So normally all these databases,
Yes.
they might be different and so on, but you just need to understand the basics. If you understand the basics of a database, you can now pick one database and learn everything you need to learn about. It will be easy. But without understanding these fundamental concepts, you won't be able to just go in. Somebody will wake up in the morning and say, I want to learn Oracle database. Very good. It's a very good thing to learn Oracle database, but understand the fundamentals. Because when you understand the fundamentals, from here now, you can wake up and go and learn Microsoft SQL Server. You can decide to go and learn IBM DB2. You can decide to go and learn MongoDB, whatever you want to learn, that's fine, but you need to understand these fundamental concepts that we're talking about. That a table needs, a database needs a table, a database resides in a server, and you can have many environments in your server. You can have many servers. I can have 20 servers, but this server is a replica of that. This server stores only this information, just like you can have 10 plots, right? Out of those 10 plots, this plot is only for farming. This other plot is for agriculture. This other plot is for renting property. This other plot, maybe you want to build a stadium in there. So think about it that way. Maybe another plot you want to build a mini city. Another plot is where you have your family residence and so on. So that's how you can have many different servers, and then you decide how you want to save your databases in what server. Within those databases now, you have different rooms in your house. One room is for where they cook food. Another room is for where they go to the toilet. Another room is for where you go and take a shower. Another room is where visitors come and sit and you entertain people. Another room is just for sleeping. So that's how you have those tables within your database broken up, so that one table would be for customer information, another table for order information, and so on. And then when it's time for you to answer those questions that we said, database is not just for storing information. When we want to share, we know, okay, we want to share just this one. When we want to secure, okay, we want to secure just this part. When we want to be able to get information fast, we just go directly to the table where it's located and grab the information. Okay? So that said, again, why do we need NoSQL or non-relational databases? The reason is because maybe it's faster speed, maybe of scaling, maybe you want to increase and reduce it, or it's maybe better cost to you. So that's the main three reasons why you see NoSQL databases or non-relational databases being used. But there's a new one known as NewSQL. This is a case where you don't only have SQL and NoSQL, they want it to be dynamic. I think all these guys that created those old databases before, Microsoft created SQL Server, Oracle has its own database, IBM has DB2. Now they have even newer databases because they are not out of the picture. Because these ones were created in the early years, what was it, the 70s, early on in the 70s when you had Oracle, IBM, SQL Server, and now you have all these newer ones in the 2000s. But now these big companies as well have also created newer versions, online versions, ones on the cloud. Even Microsoft has Azure. Azure has Cosmo DB. This Cosmo DB right here. Okay. Oracle has updated versions of different databases that it uses. The same with IBM. So that's what is known in this case as NewSQL, because the NewSQL was able to have these new values that are being these new types of databases, database models, because it's multi-model. One part of it is SQL, another part is NoSQL, another part is particular for a need of an industry. Okay. That said, yep. So NewSQL again, it's adopted from our RDBMS. RDBMS stands for Relational Database Management System. So it's a relational model. It has that ACID transaction. It can do SQL queries. It can also take different things from performance, scaling, and distribution. And in this case, Azure Cloud Cosmo DB is an example, and the other ones from the other companies. All right. So that said, going back again to the very beginning, before you want to start creating a database, you have to sit down with your stakeholders, sit down with the person that needs a database, and ask them these questions. Why do you need a database? What are you trying to accomplish? Okay, if it's a database for school, if it's a database for a store, if it's a database for library, if it's a database for movie rental company or movie industry, then you go ahead and maybe take a whiteboard or a canvas or pen and paper. You write down a model, write down the schema. What are some of the entities? What are some of the things that are going to be players within this database? And then you write, okay, if it's going to be a school, I'm going to have teachers, students, classes, classrooms, events that take place and so on. Maybe write that down, and then you go now to the next step, which is the creation step. You create and implement that database. And then, the guys that are building the websites or building the software for your company to be able to work, they now write SQL operations, that will be able to integrate what you have designed and built into actually a functioning product. But at the end of the day, people will come up with ideas. Maybe it should have been done this way. You can make it faster that way. So you go ahead and do maintenance. You fix it. Nothing is done once and for all. You have to keep building. You need to keep adapting, and you need to keep evolving. That's the normal way IT works. Okay. So once you monitor, evaluate, and maintain the database, it gets bigger and better, and then the cycle continues. So all of this can be done by different people within the field. So all those skills can be done by maybe the business user or the project manager or stakeholders, or you have software developers and also database administrators. That's the job that most people say, I want to become a DBA. What does a DBA do? The DBA is going to go ahead and plan all of that database life cycle that we've talked. They're also going to be able to install databases. Somebody will bring a new database, they need to install it, also configure it, create it, secure it, monitor it, all of that stuff. They do it. They also improve it, change versions, make sure that it's normalized and indexed and so on. Okay, the software developer is just there for the operations part. He's going to create software that can go in and maybe write SQL code, as you can see here, structured query language, that can actually ask questions of the database and produce reports from there. But the business users, the stakeholders, those are the guys that have the experts. They approve your project and then approve the budget to be able to create a database and run it, maintain it, and so on. Does that make sense? But there are many other roles as well, like data analyst, architect. Data analyst and data architect again might be the same as a database designer. Okay. And then there's also data scientists, which we cannot go into right now because it's a whole big topic by itself. So what questions we have? Does everybody feel like this helps you understand a little bit what databases are and how you can get your feet wet about it?
Sorry, I don't get to understand the non-relational database. I didn't get it clearly.
Okay, so the not relational database, right? So for instance, let me go back to that slide. Okay, so for instance, where is it? Somewhere around here. Okay, so databases, the relational databases are the ones that have tables that are related to one another. Okay, so we've talked about how we are going to create tables to hold all the information that we need to save for a database. But in some cases, that is not really sufficient. It does not really serve our purpose. For instance, if you were going to be storing documents in your database, you cannot really store it that way, and you cannot pull the information very fast. But because we wanted to be able to address some issues like speed, being able to scale, increase or reduce the size of a database easily, and also being able to manage the cost of the database, we went into the NoSQL solution. So NoSQL is the opposite of SQL, meaning not only SQL. These databases, they are not relational databases only. They do more than relational databases. So they have relationships, but they also are able to accommodate for higher speed, scaling up and down, also making sure that the cost is less. Why is that? Because when you start storing documents into a database, there is no way that you can really accommodate the speed, cost, and the scaling, because the databases that were created way back when in the beginning of time did not accommodate for distribution. Remember back then, everybody was mostly cared about just having a database to hold the information for maybe that school. But if you want people to be registering to your school from Japan, China, Canada, and so on, you want them to be able to access your database. You want to have distributed systems. Back in those days, the world was not a global village, so back then you just wanted a disk or a server in your server room in your back office, and then you're good. But now you want probably the server to be hosted on the cloud, and for people to be able to upload documents, because again, storage was a big thing back then. They did not have a lot of storage, but now everybody has storage. I can be walking around with 2 terabytes in my pocket, but back then you could not even have up to 1 gigabyte. Nobody could have that amount of storage, and it cost so much. But now storage is no longer uh, what should I say, bottleneck, you know. So people have a lot of storage, they have all these ideas, and you see the number of databases that have been created within the last 10 years. Number of different types of databases. But back then in the 70s, 80s, and 90s, we had less than 10 databases. But now, within 10 years, you have more than 20 to 30 databases that have been created to answer these questions that these old school databases could not answer, which had to do with oops, which had to do with storing documents, storing key values pairs, having graph databases, and also wide column stores. Does that help explain your clarify your question? Oh, I think I lost you there. Okay, I think I heard you. Yeah, so that's when NoSQL comes into play, because it is not only sufficient for us to have a relationship, we want to go beyond that. We want to be able to deal with, distributed, free-form data, flexible data that can increase or reduce anyhow, and also be able to not pay with a whole one leg and one arm. We want it to be cheap. Sounds good?
So does that mean is preferable?
So does that mean NoSQL is preferable? Not necessarily. It depends on what you want to do. Most of your questions can be answered with a relational database because that's a tradition, that's a custom. It answers most questions. But if it is something really pertinent, something really new that a relational database cannot answer, then you might need to look into the non-relational databases. But I can guarantee you that for years, as you have seen from the 70s, those databases worked then, they still work now. Even Microsoft Access. I use Microsoft Access in many different areas. I still use it today. You can use Microsoft Access to do mostly relational databases. I think it will work for almost everything in Cameroon. But now, when you start working for high-end, futuristic companies in, let's say, working for companies in military environment or in the new world orders and so on, then you need to be able to adapt to documents. In Cameroon, I don't think we even have documents that are being stored in a database, not yet. So all the basic relational databases will work just fine for most of everything, maybe 80% of that's going on right now in the world. But for the future, being able to have lots of documents stored in different places and accessing these documents, MongoDB is quite popular for that. If you want wide column store, then you think of Cassandra. If it's graph databases, because think about robotics, new things that are being talked about robotics. Maybe you want to be able to save voice recognition and all that kind of stuff with the Internet of Things that is very popular, where you call a particular name, whether it's Google or Alexa, and then a particular application or hardware answers back to you. All those will not be able to use a relational database. They will need to use a NoSQL non-relational database because they need to be able to query the information or ask questions of the information differently. Okay, so that's mostly for the newer technologies, the ones that are still being um, discovered and being presented. Make sense? I think you're on mute if you're speaking. So yes, what other questions do we have? I believe, let's see. Let me make sure that I covered everything that I promised to do today. It's my window. Yes, so we just talked about SQL, NoSQL, new SQL. We talked about relational versus non-relational databases. We talked about what the CRUD is, creating, reading, updating, and deleting data from a database. And every transaction in a database has to be atomic, consistent, isolated, and durable. So we've covered every major thing in our outline for today. Do we have any questions? Again, all these notes are available for you um, online. And we talked about the core database features, database management systems, or relational database management systems. And we talked about some examples like the school or store, let's say e.g. store, which has customers and so on and so forth, a school that has students and teachers. And your database can be on-prem, which is known as on-premises, or on the cloud. Pretty much a cloud. What is a cloud? We'll talk about that next week. Even if it's on the cloud, it means it's just stored on somebody else's computer, not on your computer. Okay? We talked about relational database management. We talked about what a server is. A server is where you actually store multiple databases, and the tables that are made up for, or that are the building blocks of databases, right? And each entity in your real world scenario usually is a table, and the tables are made up of columns and rows. To define a table, you give the table a name, for instance, a given name, date of birth, and so on and so forth, and then a particular type. The data type in this case would be, is it a number, is it a date, is it an integer, is it a decimal place, is it a percentage, and so on and so forth. Then we talk about primary key, column, and also foreign keys. Okay. What questions we have? Anybody got any questions?
Yes.
Go for it.
So I've understood all what you said about I don't well understand I have not well understood primary key columns.
Okay, awesome. So let's go back to that. So normally a table is made up of columns, right? And because the table is made up of columns, we want to be able to identify each one of our records. Okay? So each one
Yes.
of our records needs to be identified. For instance, you are a record in the Cameroon identity database. If you have a passport, you are a record in that passport database. If you're a student in a school, you are a record in that student table. If you're a teacher in a school, you're a record in that teacher table in the database. How do we identify you? I cannot say that, you can identify me by my first name because there might be more than one John or more than one Mary. Or the last name, maybe you have more than one family members in there. That's not the best way to identify people in this world. To identify records, you have to come up with a unique value. So the key there is a unique value. If you give a column, you know that this column is going to hold the information about a person. So let's give it a person's name, a person's date of birth, the person's color, the person's height, the person's, all the different features that you can have. And then we go ahead and add another column which will be generated automatically and say this column is going to be the customer ID. And then we set the column to be increasing by itself. Each time we add a new customer, we add the number by 1. So if I go here and I add a new customer, Vitus, the new customer's number is going to be 449. And then it's going to have all my information on there. If tomorrow they ask, where is customer number 449, it's always going to be me. But if I come in and say, who is customer number Dora, or who is customer with the first name of Dora, there might be 10 of them. So that does not identify them uniquely. So you need a key, it's like an ID, to be able to identify every record on your table. Now, when you have that key, everybody is going to know that the moment I say 567, I'm referring to that customer ID. So I don't need to be repeating that customer's information everywhere. When it's time for me to create an order, I know that this order is for Leilani Santos. I just go ahead and put customer ID 567. And then tomorrow I can join these tables. I'm going to be able to join the tables and get all the information I need for the order, as well as maybe the address and so on and so forth that you need to send the order to. Does that make sense?
Yes.
Yeah.
Yes, it does.
So yeah, it's just like you have your car. Your car has a key. You take your car and park it somewhere. You remove the key. You're walking around with that key. That key signifies your car, but you're not walking around with the whole car. When it's time for you to move to the next place, you use that same key to start your car and move to the next place, just like that. So the key is the primary key. It's unique. Not your car key is not supposed to start somebody else's car. Somebody else's car key is not supposed to start your car. So every key is unique for every record on a table if it's a primary key. Sometimes you might try to say, oh, we wanted the email address to be the primary key. That's not a good practice. When you design your table, you don't want to use that. Because what if I decided I want to have two records in that table? What if somebody else is using my email address as well? You cannot force people to do things to be able to make your table to work. You have to force yourself to do things to make your table work without having to bother those that are the users that are going to be using your table. Does that make sense?
Yes. Yes.
Good. Very, very, very good questions. What other questions do we have? No more questions? Nobody else got any questions? All right, so that is it for class today. Let me go back and see if I can find our schedule so that we can review it one last time. Next class is going to be next Saturday. I will let you know during the week if we're going to have issues with that class, because I might not be able to. Yeah, we'll see. I might have to record the class, but it's going to be a very short class. So 5 p.m. on Saturday, July 30th, we're going to have our next class. Okay, it's going to be on cloud computing. Again, we're not going to learn any particular cloud system. Most people know about AWS. Just like today, we did not learn about any particular database. We want to just understand the foundational knowledge so that from there, you'll be better placed to go around, and you've known what databases are. You can pick one database and run with it. You know what cloud computing is about. You can pick one and run with it as well. Okay? So any more questions? All right. So again, we could have that. Yes. No questions. All right. So well, that is it for the day. I'll let you guys enjoy the rest of your evening while I get started, and we'll be in touch. Have a wonderful weekend. All right.
Same to you.
You too. That's it.